Shirtless Guy 666 here, and I thought I would do another video that has to do with math and stuff. I got kind of encouraged to do that by a hater, if that's a good word, I guess. Called me out like I'm dumb or something, but those were original on my last video that had to do with this math and everything. It was original thought, and it just happens to be very difficult to make original thought seem like over the top brilliant, because you have to think of something that's not been thought of, and that makes it very hard to do. So since he made me think, well, I thought, well, then why don't I just do something that I know I do good, which is math. I went to Harvard College for 3 years. I didn't flunk out, I dropped out, and I was very good at it. So I thought I would talk about some of the math I learned at Harvard, and some of that is called complex analysis. But rather than talk about that, I'll get right into it. So there's something called complex numbers to start with. And first of all, you see this, or am I not close enough? If I take a number like square root of -1, that doesn't really exist, because no number when squared, or let's say x squared equals, wait, that's what, no, I meant it right the first time. Like the square root of -1 doesn't exist, because there's no number when multiplied by itself is a negative number. So we just call it I, because it's imaginary, and call that a square root of -1. But then what about real numbers combined with imaginary numbers? Like if I say, if I call a real number x, and I call an imaginary number I times y. So it's a number that has a variable that's real and a variable that's imaginary, because y is imaginary and x is real. But what do I call the sum or difference? It could be 2. What do I call the x plus iy? Well, that could be called a complex number, and that could be z. Z is a complex number, which is the sum of a real number like x, and which is a variable, and a imaginary number like iy, which is an imaginary variable. So z is a complex number or complex variable. And how do you plot that? Well, if x can be on one direction, like say a horizontal could be real, or x, and then the vertical direction can be I, y. And then whatever point you're at is just the real part, which is how far left to right you are, and the imaginary part, which is how far up and down you are. Get this right here so you can see that. Gosh, how to do this. So what they call this is, I like to call it the complex plane, because it's a plane, not a line, because it's two-dimensional. Planes are two-dimensional. And it's also called an Argand diagram or a z-plane. Z-plane because it's z is a complex number, but that z-plane kind of sounds like a airplane or something. And then the Argand diagram, I don't know who Argand was, but it's a complex, it's a complex coordinate plane. You could say. Man, I'm having a hard time with this angle here. Maybe I am dumb. Let's change the angle of this. Jeez. Anyway. Okay, so now let's talk about a formula. I'm having a hard time with this. I just hit something I shouldn't. Okay, there we go. Okay, now there's a thing. Another number I want to introduce is, most people know what pi is, if I can even write it. Pi is just the circumference of a circle divided by its diameter. Okay, and that's an important number, what I'm about to talk about. And then E is another number. E is a number. It's it's a number whose one of its main qualities is that the derivative with respect to x of e to the x equals e to the x. So it's a number whose derivatives is how fast a function is changing with time. Like could be call it the slope. If its slope is upward, if the slope is high, it means it's going up fast, and that's a high derivative. If its slope is low, it means it's going down more, and that's a negative derivative. Or if it's staying constant, then there's no change, and so if the derivative is zero. Well, exponential function is such that the function is increasing at the same rate as the value of the function, which means an exponential, if you have very little, it's not going up very fast. But then as you get more and more and more, it starts going up faster. So as it tends to negative infinity, the slope is zero, but as it tends to positive infinity, the slope is infinity. And this they call E is such that the derivative is equal to itself. And so that number E is before I go on, I know this sounds boring, but it's going to get a little bit better in just a minute here. So pi is an irrational transcendental constant. It's both those two things, and it is equal to 3.14. I think have more room to write this. Pi is about 1.4159265. It goes on and on, never resolving, as Spock said. E is similar, but it's not the same value, but it's the same type of number. It is equal to 2.7182821828828. So it's 2.718281828, but it doesn't repeat that forever. That just happens to be a coincidence. Okay, they're both irrational and transcendental constants. So now the real fun, if this is fun, I'm going to talk about something called there's something called Euler's theorem. It comes from the fact that e to the x in Taylor series, e to the x can be broken down into components. That's a series, and then the sine of x can also be broken down, and then the cosine of x can be broken down into components. And if you take the series expansion or Taylor series for e to the x and plug x equals I theta, that's not theta, I theta, which is a Greek number, into e to the x, then you will find that some of the terms are are even powers, and some of the terms are odd powers, and I forget which is which, but it turns out that all the evens or all the odds turn out to be cosine of theta, and all the other ones, whether they're odd or even, which way it goes, turn out to be I sine theta. So it turns out that the Taylor expansion series, expansion of e to the x, shows that e to the I theta, which is now is equal to cosine theta plus I sine theta. That is called Euler's theorem. It comes from Taylor series, and like I just said, so Euler's theorem is e to the I theta equals, not theta, e to the I theta, let me make more room here, I gotta write this better, e to the I theta equals cosine theta plus I sine theta. Okay, that's Euler's theorem. Okay, I mean, not theorem, I should say formula. Sorry, my bad. When I said theorem, I meant formula. My little goof there. Euler's formula. So how do you interpret that on what's called, like I called the complex coordinate plane? You have x, which is real, iy, which is imaginary, and you have e to the I theta equals cosine theta plus I sine theta. And so theta is an angle, and it is it's measured from the x-axis and then going counterclockwise. So if the angle is 0, you're right here. As the angle goes positive, it goes in the counterclockwise direction. If it goes negative, it goes into the counterclockwise direction. And the angle is measured not in degrees, but in radians. So radians are, however much arc is measured out as the angle changes is how much radians you have. And so if the radius is 1, then because of a whole circle you have the circumference of a circle is pi times d, but d is 2 times radius, so d is 2r, so the circumference is pi times 2r, or yeah. So if the radius is 1, then a whole circle around the whole circle would be 2 pi radians, because 2 pi times r is 2 pi, and I said that it's however much it marks out as the angle. So if radius is 1, so let's say this is 1, then this would be I, this would be -1, this would be negative I. So if the radius is 1, the angle of what we call 90 degrees would be 1/4 of 2 pi, which is pi over 2. That's pi over 2. And then the radius, and then the angle of what we call 80 degrees would be half of the circumference, and that would be half of 2 pi, which is pi. That's pi radians. Negatively, ¼ turn backwards would be negative pi over 2 radians, and a whole turn backwards would be negative pi radians. Or if you keep going this way, you would get 3. This angle right here would be 3 pi over 4. So it's 3/4 of pi, and then all the way back around is 2 pi. And the numbers, some of the numbers are the same, because any multiple of 2 pi is equal to itself. So 0 is equal to 2 pi, which is equal to negative 2 pi, because we both no matter how many times you go around the circle, I could say this is angle 0. It's also angle 2 pi, or 4 pi, or 6 pi, or 8. So even though those are different numbers, any multiple, any numbers that are difference by a multiple of 2 pi or 2 pi itself are equal. But that's not the point right now. So I'm gonna say that now that we talked about Euler's formula, now we're going to talk about Euler's identity. What's a special case for that formula? Euler's formula. If I have the compass coordinate plane here, this is the x coordinate, this is the y coordinate. Now, let's say that let's say I have a circle, because that's how it works. And if the circle, let me see how to say this. If the circle, if this part is this part right here is cosine theta, and this part is I sine theta. Okay, and we know how do I put this? we know from we know from trigonometry that if this is a right angle, then we know that if this is cosine theta, this is I sine theta. We know that let me think, how do I say this? Let's see. I was going to say this. R just equals 1. Okay, here's what we do. We take the we take I want to show that Euler's formula for I theta equals cosine theta plus I sine theta is a circle of radius 1 around the complex coordinate plane centered at the circle at the center. And one way to do that is that how do I say this? This is 1. That would be 1. That'd be square root of 2. Okay, that's how I'm going to play it. If you have okay, thanks for that time to think here. If you have e to the I theta equals cosine theta plus I sine theta, then I'm going to play it. I was going to do in discrete number, I won't. If theta equals 0, then you have e to the I theta equals cosine theta, which is 1, plus I sine theta, which is 0. So you would have for e to the I for theta equals 0, e to the I theta is 1. If theta is equal to pi, then you would go, then the angle would be, let me write that out just so you know. That's what I'll do. You already seen the graph. Let me explain it in math terms now. So if theta equals 0, then e to the I theta equals cosine 0 plus I sine of 0. And since cosine of 0 is 1 and sine of 0 is 0, then you have e to the I 0 equals 1. So that's consistent with, well, the graphical version of it. Now I'm going to do 2 examples here. The first one is from Eulers Identity. So for Eulers Identity, I'm going to let like you say, they say let in math. Let theta equal pi. Okay, let theta equal pi, and if theta is equal to pi, then you have e to the I. Well, let's write the equation first. E to the I theta equals cosine theta plus I sine theta. And if theta is equal to pi, then e to the I pi equals cosine pi plus I sine pi. Okay? That right there. And since cosine pi is 0, I mean, wait, sorry about that. Since cosine pi is -1, because that's the real value, the real axis version. You know, cosine pi is -1, and sine pi is 0. So you have e to the I pi equals -1 plus 0 equals -1. So you have, I'll write it down here, e to the I pi equals, okay, cosine of pi, which is -1, plus sine of pi, which is 0. So that means e to the I pi equals -1. Okay, we're almost there. And graphically, that would be because on the graph, an angle of pi would go half a circle, and that's the value here is -1 on the complex graph, because the imaginary value is 0 and the real value is -1. So I get this. We're almost here. E to the I pi equals -1. What does that mean, though? Put pi on the other side, you have e to the I pi plus 1 equals 0. And that's called Euler's identity. Hope you see that. I hope you had followed me too. So e to the I, let's take this part out. E to the I pi plus 1 equals 0. That's very profound. I mean, nobody really knows what it means. They just know it's true. Why is it cool? Well, first of all, it's got a lot of important numbers. Remember the numbers I mentioned at the beginning? First of all, it's got 0, which is the additive identity. Means add 0 to any number, it stays the same. You got 1, which is multiplicative identity. Multiply any number by 1, it stays the same. But you have these three numbers, e, I, and pi, which I mentioned at the beginning of the video. Well, those are three very important numbers, pi, I, and e. So it has these three important numbers plus 1 and 0. So it's got 5 of the most important numbers in math. It's also got addition, because here you have this number plus that number. It has multiplication because you have I times pi, and it has exponentiation because it has e to the I pi power. So it has addition, multiplication, exponentiation. It has 0, 1, e, I, and pi. And it's got an equal, which means it has an identity. It's actually it actually is an equation. That's incredible. And nobody really knows what it means. That's called Eulers. This is hard to write this. I'll give you more room here. Eulers identity. That's what that's called. Okay, it's been mentioned in its famous identity. It's even mentioned in an episode of Rizzoli and Isles, where Maura Isles says she likes Euler's number and its identity. It's mentioned in Person of Interest, when the character played by Michael Emerson, I forget his name, Finch or something, says this equation is like a sonnet. He says that in one of the episodes. Anyway, now the last thing is a related identity. I said we'd do that. Well, let's say instead of making theta 0 or pi, make it theta pi over 2. That's a quarter of revolution. And that would make it equal to I, because here, if it goes a quarter turn around the circle, the real value is 0, but the imaginary value is I. So that would make it imaginary and equal to I. So that would basically say that e to the I pi over 2, because a quarter of relation is equal to 1/4 of 2 pi, which is pi over 2, because half of 2 pi is pi, and half of pi is pi over 2. So e to the I pi over 2 equals I. See that? Because you could also look at it as e to the I pi over 2 equals cosine pi over 2 plus I sine pi over 2. And cosine pi over 2 is 0. And I sine pi over 2 is I, because sine pi over 2 is 1. So 0 plus I is I. So that basically means that e to the I pi over 2 equals I. I hope I put that in an okay place there. Should write a little lower. E to the I pi over 2 equals e to the I. Let me write that a little better. E to the I pi over 2 equals I. Okay? I explained it graphically and I explained it with the Eulers theorem directly, numerically. Let's take that somewhere. So what we have is e to the I, it doesn't look like I, e to the I pi over 2 equals I. Now the related theorem, the related identity is, what if I take the ith power of both sides? So here I have e to the I pi over 2. Sorry, I put that napkin in the way. E to the I pi over 2 to the I power. So that would be all this to the ith power. Okay, that's pi over 2 here if it doesn't look like it. E to the I pi over 2 equals I to the ith power. So that's an imaginary number to an imaginary power. And it's equal to e to the I pi over 2 to the I. But in math, we know that any number to an exponent, any number with an exponent taken, with a whole number is taken to an exponent, is equal to the first number with the two exponents multiplied. So you have e, that this is within, then e, this would then be equal to e to the I pi over 2 then times I is equal to I to the I. And e to the I pi over 2 times I is equal to e to the I squared times pi over 2. E to the I pi over 2 is equal to e to the I squared pi over 2, which is equal to I to the I. What's I squared? We said at the very beginning of the video, let's keep going. Almost done here. So what we have is, so far, we have e to the I pi over 2 times I equals I to the I. But that's equal to e, but to the I squared pi over 2 equals I to the I. But I said before that I equals the square root, that's hard to write, man. Square root of -1. If I is the square root of -1, then I squared is the square root of -1 squared, which is -1. So I squared equals -1. So in this equation here, e to the I squared is -1. So that's e to the -1 times pi over 2 is equal to I to the I. But e to the -1 times pi over 2 is just get that napkin out of there, is just e to the minus pi over 2 equals I to the I. So what we have then, this is the final bit here, e to minus pi over 2 equals I to the I. Now what's interesting about this is that, dang man, what's interesting about this is that this is an imaginary power to an imaginary power, but it's equal to a real number because all the numbers here are real. E negative I negative pi over 2 is a real number. So the imaginary power of an imaginary number is actually a real number. And I could rewrite it by just saying I to the I equals e to the minus, I have room here. Let me do this. Let me get more room. I to the I equals e to the minus pi over 2. And that's brilliant because it's got some important numbers. It's got e and pi. It has I too. So it has all the same three numbers that the last identity did. And just for fun, e to the I minus pi over 2 is also equal to 1 over e to the pi over 2. One over e to the pi. 1 over e to the pi over 2. And moreover, it's power over root. So e to the pi over 2 is also the square root of e to the pi, because the over 2 just makes it a square root, and the e to the pi stays the same, so it becomes 1 over e to this 1 over the square root of e to the pi, which means finally, last step, that I to the I equals 1 over the square root of e. It's fun if I could write e to the pi. And that is a related identity to the others I've mentioned in this video. That an imaginary power to an imaginary power is equal to a real number, which just happens to be 1 over the square root of e to the pi, instead of got a real value. So that's it. That's interesting. I'm the cap to my pen here. I think it's right here. So I have three formulas here. There's Euler's formula, there's Euler's identity, and there's a related identity. Euler's formula, to just recap, is e to the I pi equals no, not e to the pi, I'm getting tired. E to the I theta equals cosine theta plus I theta. That's Euler's formula. Euler's identity is e to the I pi plus 1 equals 0. A related identity is I to the I equals 1 over the square root of e to the pi. I called that video with those three titles. Thank you much for watching, and please have a great night. Talk to you later. Bye-bye.